Alright, so in this video what we are going to be talking about is section 15.3, and 15.3 is on colligative properties. So before we get started, I just want to go over the objectives for this section. The first objective is to explain the nature of colligative properties. The second objective is to describe the four colligative properties of solutions. And then the third and final objective of this section is to calculate the boiling point elevation and the freezing point depression of a solution. So let's go ahead and get started with what a definition of colligative properties is. So the colligative properties are defined as the physical properties of solutions that are affected by the number of particles but not by the identity of those dissolved solute particles. So what I want you to do is write what I'm about ready to write down. I'm just going to write down that definition that I just stated. So, as I wrote this here, I want to emphasize one thing, and that's this item of number of solute particles. That'll be especially important when we talk about boiling point elevation and freezing point depression. So, with that definition in mind, we are going to talk about the four colligative properties, and I want you to copy these down in the spaces provided. So, the first of four colligative properties is vapor pressure lowering. The second colligative property is boiling point elevation. The third colligative property is freezing point depression. And then the final physical or colligative property is osmotic pressure. Now, before we talk about each of these four colligative properties in details, what I want to do is identify what the difference of an electrolyte versus a non-electrolyte is. And this will help us with that boiling point elevation, freezing point depression later on. So all I'm going to do here is divide my paper in half and separate out the electrolyte from the non-electrolyte portion. So an electrolyte is a compound that completely dissociates in water. Now, the word dissociates here, all this means is that it breaks apart. So if something is an electrolyte, when we dissolve it in water, it's going to split into its individual components. So an example of this is when we dissolve salt in water. What happens when we dissolve salt in water is that it splits apart or it dissociates completely. So this NaCl will break into Na plus ions and Cl minus ions. Now, this is only going to occur if we have an ionic compound. So keep that in mind as we go through some examples. The other type of item I want to talk about is a non-electrolyte. So in a non-electrolyte, there is going to be no dissociation occur when a substance dissolves. So I'm going to simply put dissolves but does not dissociate. So this happens in covalently bonded substances such as sugar. So our example here that I will show you involves sugar. So the simple formula for table sugar is C6H12O6, and that's a solid compound. And if we would add that to water, what would happen is this. We wouldn't have a chemical reaction. Now the sugar does dissolve, but what would happen is that this particular compound of sugar would become an aqueous solution. Now notice how there is no difference in the sugar compound or the sugar formula before and after this process of dissolving occurs. Those are things that you need to keep in mind as we go through this process. So moving on, what we are going to talk about is the 4 properties of colligative properties. So vapor pressure lowering. The definition is exactly how it sounds. This right here, this colligative property, is going to lower the vapor pressure of a solution. Now this lowering is in comparison of that pure solvent of that solution. So we're going to draw a couple pictures to depict what I am saying here. We're going to start out with pure water or pure H2O, and I'm going to draw a beaker. So in this beaker of H2O, we are going to have several water molecules in this scenario. Now, this is pure water, a pure substance. We will talk about the difference between a pure substance and a solution. So let's say in this beaker over here, we have a solution of sodium chloride that is dissolved in H2O. What happens here is this. The sodium gets separated out from the chloride, and what happens here is that process of salvation occurs, and so we get the water to surround each of these ions, and so the water surrounding each of these ions would look like this. Now, the same thing would happen for the Cl. This time the H's would surround that Cl ion. So a couple of things here occur differently or cause the vapor pressure to lower on this sodium chloride solution here on the right. So number one, the water surrounds the Na plus and Cl minus. What this does, by the water completely surrounding the Na plus and the Cl minus, is it does not allow for as much H2O to become a vapor. So when we're heating these two solutions up, what happens if we apply the same heat? This beaker on the right is not going to have as many pieces become a vapor. Now, as a result, if there's less H2O as a vapor, that means the vapor pressure is going to be lowered. So I'm going to add one more point to this property here. So less H2O as a vapor means that we have the vapor pressure lowered. All right, so now we talked about vapor pressure lowering. We are going to move on to boiling point elevation. So what happens in a solution? The boiling point is actually raised compared to the boiling point of the pure solvent. So what happens here? What we're interested in is the formula for this particular process. So the formula for boiling point elevation is this. Delta TB equals KB times M. So what each of these terms mean is as follows. Our delta TB is our change in boiling point, and this is expressed in degrees Celsius. Now, this is the change compared to that of the pure solvent. The KB is the boiling point elevation constant, and it is in units of degrees Celsius per M for molal. Now the last thing in this formula is our M, and this is the molality of the solution, which again, molality is expressed in little m, and we'll talk about that here in a second. Now, freezing point depression, very similar to boiling point elevation, except depression is going to lower the freezing point of the pure solvent. Now, the formula is very, very similar to that of boiling point elevation, and it is as follows. So, the formula here, again, very, very similar, except our F's replace our B's. And so, to go over what these means here, the delta TF is the change in freezing point compared to that of the pure solvent. And again, this is going to be in degrees Celsius. Our KF is the freezing point depression constant, and that is going to be in degrees Celsius per M. And then the M is also going to be the molality of the solution. And that is going to be in little m for, again, molality. All right, so let's go ahead and go through an example problem using these two formulas that we have here. So we'll transfer to this third page, and I just want you to read that problem over, and then what we're going to do is we're going to go work through the example together. All right, hopefully you had time to read through that problem, but what we're going to do, we want to know what is the boiling point and the freezing point of a 0.029 molal aqueous solution of sodium chloride. So before we even get to the formulas of boiling point depression, boiling point elevation and freezing point depression, we need to talk about this sodium chloride. So sodium chloride, when it is dissolved in water, what actually happens is that it is an electrolyte. So what that means is that sodium chloride is actually going to break into Na plus ions and Cl minus ions. So what this means is that we have to consider the molality of the entire compound here, and we have to do a little work to find out the total molality of this particular solution. So we start out here with 0.029 little m, and what this means is that we have both 0.029 molal of Na plus ions, and we have 0.029 molal of this Cl minus. So when we use our molal and our freezing point depression and our boiling point elevation, what we're going to have to do is add these two numbers that I'm boxing in together. So when we add these two numbers together, we end up with a total molality of 0.058 m. So what we are going to have to use whenever we refer to molality is 0.058, and that's because NaCl broke into two different pieces. That's why this number doubled. So let's jump into the boiling point elevation first, and then we will do the freezing point depression second. So the formula for boiling point elevation is delta TB equals KB times M. So delta TB, nowhere in the problem did it say anything about the temperature changing degrees Celsius. So ultimately this is going to be our big question mark that we go after and we find. Now our KB, these things are constants and they never change. So we can find those in the deluxe periodic table packet that I gave you at the beginning of the year. So if you turn in the page, and it's starting to get towards the end of this particular page, you will come to a chart that says our molal freezing point depression and boiling point elevation constants. Now, we are dealing with an aqueous compound, which means that this particular solution has a solvent of water. So on this chart, what we are going to be looking for is the Kb of water. So if you scroll over here, you'll find water, and the Kb for water is 0.512 degrees Celsius per m, or per molal. So I'm going to write that down, but again, that number came directly from a chart that you will get on test. So our Kb is 0.512 degrees Celsius per m. Now, our molality, we just got done talking about what the total molality is, and it is that 0.058. So I'm going to insert that value into our last component of this formula. Now we have two of the three parts. We are going to solve for that change in boiling temperature. Okay, so to calculate this particular problem, all we need to do is take 0.512 and multiply it by 0.058. When we obtain this, we get a change of temperature of 0.0296, and what I'm going to do is I'm going to round this to 0.030 degrees Celsius. So our change of boiling point is 0.03 degrees Celsius. Now we're not quite done. We want to know what is that new boiling point of this solution. So if we look back on this particular chart and we go to water, we find that the normal boiling point is 100 degrees Celsius. So what we need to do to find out the new boiling point, and I'm going to label this as boiling point, BP, we have to take the original boiling point, which was 100 degrees Celsius, and we have to add what was elevated to that particular boiling temperature. So our new boiling point becomes 100.03 degrees Celsius. Now we're going to do a very, very similar type of problem, but for our change in freezing point. So if you can remember, the change of freezing point is equal to the freezing point constant times that m for molality. So again, nowhere in the problem did it say anything about this was the change in degrees Celsius for this solution. So ultimately, this is going to be what we're finding out. The Kf is a constant, and again, this constant can be found right on this chart. So we're under Kf's. We are looking at the solvent of water, and we have a value of 1.86 degrees Celsius per m for molal. So I'm going to write down 1.86 degrees Celsius per molal. And then our molality, we spent the beginning problem talking about our molality, is still going to be this 0.058 m. So we have two of the three variables. What we do from here is we plug this back into our equation. So we take 1.86 degrees Celsius per m times 0.0558 m. So again, to calculate this, all we need to do is we need to take 1.86 times 0.058, and we get a change of our freezing point to be, and I'm going to round this to 0.11 degrees Celsius. Now we're not quite done because we have to see what the freezing point actually is. So we look back on this chart and we find the original freezing point of just pure water is 0 degrees Celsius. So to find the freezing point depression, what we have to do is we have to start out with the original freezing point, degrees Celsius, and for freezing point, we actually subtract that change in freezing point. So we are going to take 0 minus 0.11, and so our freezing point, or our new freezing point of this solution, becomes negative 0.11 degrees Celsius. Now, that's the only math problem for the section. There is a lot of formulas, a lot of thinking about what has to happen for this process. The last colligative property that we will discuss is going to be osmotic pressure. Now, osmosis is the movement of water through a semi-permeable membrane. So it's a biology term, and so we have to think about this. This right here is the pressure caused by the movement of water. So what we're going to do here is we're just going to draw a little bit of a picture. And I'm going to use this U-shaped tube, and I'm going to put some things in it. So the first thing is this. What I'll do here is I will make this my semi-permeable membrane. So what that means, a semi-permeable membrane, is that some things can go through it, other things cannot. We also have a couple of things to think about. On this left side, I'm just going to put some dots around here, and on this left side, this is going to be our pure substance, and we're going to call this just water. Now on our right side, we are going to have a solution. So that solution is also going to have water. So I'm going to put some of these dots in here. And then I'm also going to put some solute particles, which I'm going to represent with a red marker. So scattered or dissolved in the particular solution is those solute particles. What happens here? By the nature of osmosis, water moves from an area of no solute or little solute to an area of high solute. So what happens here? This arrow that I drew is the movement of water. Now, the osmotic pressure is caused by the movement of this water. So I'm going to put one more note here and then we'll be done. So that water that's moving causes that osmotic pressure. All right, that concludes everything in section 15.3.